Welcome back. We are aiming here to complete our assembly of the global matrix vector equations and talk about the final Dirichlet boundary conditions. So, to do that, let's get on to the contribution that we have not yet tackled for the global equations, and this is the contribution from the Neumann or the traction boundary term. Okay? So the contribution to global matrix vector equations from the traction, right? And remember, the traction is simply our Neumann boundary condition for this problem. Right. So the term that we are talking about is this one. Sum over I, right? I running over the spatial dimensions, right? Sum over I, sum E belongs to E Neumann, right? Sum over A, that's all the nodes in that particular element, right? We have here C, A, I, E, F, T bar. We have the A index there, we have the I index there, and we have the E index here. Okay, what I'm going to tell you in one fell swoop is that this is going to show up as C transpose F T bar, right, globally. Okay, and I will write down in the next line the detailed construction of the F matrix. And in order to do that, I am going to take, I'm going to write here first the C transpose vector as a row vector. Okay, and I'm going to give myself plenty of room for it here. Okay, and the idea is that multiplying it is our FT bar vector. Okay, and here too, let me give myself enough room. Okay, so let's construct C. Sticking with the same assumptions I'd made before, we have a contribution from the very first numbered global node, okay, because I'm assuming that, or I'm considering the case where we do not have Dirichlet boundary conditions on any degree of freedom on the first node. So we have C1, okay, and we're working with the outer sum first, right, the sum over spatial dimensions. So I'm setting I equals 1, and that is the one that shows up here. Okay, and that comes from some element, right? The fact that we're doing a sum over elements is already accounted for in the fact that we have this global node here. Okay, right. So that contribution would be F T bar let me see, it would be local node number 1 for that element. Okay, and since we're talking of global coordinate direction 1, we would have a 1 here. Okay, it's going to be some element, let's call it, let's just leave it as E. Okay, and let's go on now with this. And actually, in going on, let me also use the same numbering that we used in order to construct the stiffness matrix and the F internal force vector. Okay, so I have before me here those two elements, omega E1 and omega E2, and you probably noted them down in your book or your notebook. So I would encourage you to go back and look at those, okay? Because what I'm going to do now is look at the contributions to global node A. Okay, so let's suppose that global node A shows up here along the C vector. Let's suppose that B shows up here. Global node C shows up there, and global node D shows up there. Okay, so that's A is going to be here, B, C, D. Okay, now we start out as I did for this very first degree of freedom. We start out with the spatial dimension 1. Okay, so the global node here, right, is C A 1. Okay, and let's suppose that on this force vector, A shows up here, B shows up there, C and D. Okay. Now, the only way we would have a contribution from the A node is what? Okay. What we need to have is that the local, what we need to have is actually, we can talk of it in terms of the global nodes also. Global node A, right, lies in partial omega T bar 1. Right? That's the only way we would have a non-zero contribution to the F vector from global node A. Okay, so let's assume that this is true. Let's consider the case where A does lie in partial omega T bar 1. Okay. All right. So if you go back and look at that figure that I drew back there two or three slides ago, what I'm saying is that node A from that figure does indeed lie on partial omega T bar 1. Okay. So we would have a contribution then from element E1, and the contribution from element E1 would be F T bar local node 6, right, spatial dimension 1, element E1. Okay, right. Now element E2 also would have a contribution here, right? So we would have F T bar, right? From element E2, the contribution would come from local node 5, okay? The spatial dimension would still be 1, right? And of course is element E2, okay? So this would be the situation if I'll reproduce that figure of two elements somewhat modified. Right, so again we have omega E1, omega E2, right, and I'd label those nodes as A, B, C, and D. Okay, what I'm saying now is that let us suppose that these surfaces, right, that those are the sort of front surfaces of both the elements, right, belong to partial omega t bar, sorry, actually let me write this properly. Okay, both those surfaces I'm saying belong to partial omega t bar, okay, 1. All right, okay, right, and then in terms of local numbering, what I'm saying is that let me identify the surfaces I'm speaking of here. Okay, for element omega E1, that's nodes are 1, 2, 3, 4, 5, 6, 7, 8, and for omega E2, the nodes are 1, 2, 3, 4, 5, 6, 7, 8. All right. Okay. So we would have those two contributions, right? Let's suppose then for omega, for the Neumann boundary in the 2 direction, right, which means the degrees of freedom are being controlled in the 2 direction. Sorry, not the degrees of freedom, but the traction components in the 2 direction are being controlled on the other surfaces, right? So let's suppose that it's on this surface and it's on this surface, okay? So let's suppose that this belongs to partial omega t bar 2. This also belongs to partial omega t bar 2. Okay, so can you think of which surface? Do you see which surface I'm saying belongs to partial omega t bar 2 from element E1? It is the 5, 6, 7, 8 surface, right, of element E1. On element E2 also it's a 5, 6, 7, 8 surface. Likewise on element E1, the 1, 2, 6, 5 surface belongs to partial omega t bar 1, and in element E2, which one is it? It's the 1, 2, 6, 5 surface. Okay? All right. So if we are clear about that, let me put in the contributions then. All right. So for the contributions from the 2 direction to this traction force vector, would there be anything from node A, from global node A? There would be, right? So we would have a CA2, okay? And that would show up now right here, right? It would be F T bar global spatial dimension 2, right? We would get a contribution from element E1, right, from its node number 6, okay, right, and we would get a contribution F T bar global 2 direction element E2 local node number 5. Okay. All right. Which other nodes would contribute? So let's look at node B. Okay. What contributions would it have? It would only have contributions from the 2 spatial dimension, right? Spatial dimension I equals 2. All right. So for this node, we would get a contribution from C, B, let's put the CB1 contribution, then let's talk about the CB2 contribution. Since the CB1 contribution, right, on that node is 0, right, there is no contribution to the traction there, right, we are not controlling the traction there, okay, but that's a free surface, right, because that is a surface on which a traction may be specified, right, we've just not specified the 2 component there. So when it comes to the B node, we get a 0, okay. The contributions that do come there are from the 2 direction, and we have then F T bar. We are talking the 2 dimensions, so we have 2 here. We are, okay, let's look now at the contribution from E1. From element E1, which local degree of freedom contributes there? It's the 7, okay. From element T2, element E2, the contribution along the 2 direction, right, would be from local node 8, okay. All right. Now, let's suppose that no other boundaries of these 2 elements correspond to Neumann boundaries for the global problem, okay. That means that if we go ahead and look at CA3 as well as CB in the 3 dimension, right, we would get zeros, right. So here we would get a 0, and here too we would get a 0, okay. All right. Let's see what node C does. As I've drawn it, what traction surface does global node C lie on? Right, also on the global spatial dimension 1 surface, right? So when we come back here, we have C, and unfortunately the global number of that degree of freedom is also C, but hopefully we can cope with that repetition. Okay. There is going to be something from the CC1 direction, right, from the 1 direction there. So we move along, right, and when we come to the C node, we get a contribution of the form F T bar along the 1 spatial dimension from element E1, right. So which node from element E1 contributes? It's the local node 2. From element E2, which one is it? Local node 1, okay. Now, as I've drawn it for node C, right, global node C, there are no other spatial dimension, no other traction boundaries that contain that node, okay. Right. So what that says here is that for C, C2 and C, C3, I would get 0 and 0, okay. So let's just complete this particular line that I wrote. Global node A lies in omega t bar 1. C also lies in partial omega t bar 1. B lies in partial omega t bar 2, okay. But you note that the way I've drawn it, A lies in this and in partial omega t bar 2, okay. There's a partition there, okay. So A is of the way I've drawn it, node A is the only one that lies on 2 traction surfaces, C lies on 1 and B lies on 1, okay, and which ones they lie in has been written, has been denoted here. So, and furthermore, for the way I've drawn it here, let's suppose that D belongs to no traction boundary. D lies in none of the boundary subsets. Partial omega t bar I, where I equals 1, 2, 3. Given that, what contributions would we find in this traction force vector for global node D? You're right, all zeros. So we get a 0, 0, 0, and we would go on. So, hopefully, this process has given us some idea of how to construct this global traction force vector. Okay, this is what we are calling it, Ft bar. Okay.